page 1, number 1. This problem shows video capture of two cars, and each of the pictures, this picture, that picture, that picture, that picture, these are frames of the video. Video camera takes a bunch of pictures. Most video cameras take 30 pictures every second. So this would be first picture, second picture, third picture, and the time between each of the pictures is the same. They go click, 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 and they take the pictures at an even rate. So the car that's accelerating is car A, and you can tell that because between every picture it moves farther. So it moves a short distance between these two pictures, a little longer between those two pictures, longer between those two. And since the time between the pictures is the same and the distance is getting longer, the car has to be moving faster. So this here, it's going a greater distance in the same amount of time that it took it to go that distance. So here it's going a short distance in a 30th of a second. Here it's going a longer distance. There it's going a longer distance. This is speeding up. This is accelerating. So the way I wrote my answer out earlier was it travels a greater distance between each successive pair of photos. So I've got something about distance in there. That's important. And then I say that the time is constant. The time between each photo is the same. Time between photos is constant, so it must be getting faster in order to be traveling farther. So I'm really looking for these two bits of information. The distance is growing, but the time between the photos is the same. Those two things put together show you that it's got to be getting faster. With this car, the time between the photos is the same, but it's the same distance every time. So the car is not moving any farther during that amount of time, so it's not getting faster. It's going the same speed. Number 2, I've got a ball that's thrown directly upward. First of all, as I've mentioned before, if I could do it, I would make a diagram where the ball goes straight up and straight down. But you can see my two arrows are on top of each other, and it just looks like a double-ended arrow. So it looks like this, and then a little later it should look like that. You know, you can't really do that. So that's why I draw the diagram to look like this. It's not really going up and over and down. It's just going up and down. Let me put the blank one up. What you have to do here is just fill in all the data. What we're given is that the time in the beginning is 0 seconds. Goes up into the air to some highest point, comes back down, and at the end the time is 8 seconds. So I'm going to start filling this in. If it takes 8 seconds for it to go up and down, we know that the two sides here, the upside and the downside, those are symmetric. This is like the mirror image of that. So if it goes, this is the first half of the trip, that's the second half of the trip, the time here has to be 4 seconds. So 4 seconds up, 4 seconds down gives us the 8. You could just divide that by 2 and you've got the answer. The velocity up at the top, we could fill that in. It's a little weird. Maybe I shouldn't do that yet. Maybe what I'm going to do here is make a little graph. And I did this in one class and it seemed like it was maybe helpful. So what I'm going to do is make a graph of the velocity of this thing as time goes by. So this is going to be velocity 0. Here's time, 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7, 8. And it's kind of premature, I guess. Maybe I should come back to this. Let me set up my graph and then I'll come back to it. So this is the time. And then on this axis, I'm going to have distance. No, not distance, velocity. And that's going to be meters per second. This is going to be seconds. So velocity is 10, 20, 30, 40, 50. I'm not going to use all these, but might as well do this. -10, negative 20, negative 30, negative 40, negative 50. Now it just kind of occurred to me that it's probably best to set this aside and wait until I figure some stuff out and then come back to it and fill it out, because in order to really fill it out, I've got to pick a starting point, and I'm going to pick that based on what I find out in the problem. So we'll come back to that. This graph is going to represent what's going on here. Now, the point of the graph is really to drive home what I'm about to say, the most confusing aspect of this, which is when something leaves the ground, if this is the ground, something starts to, there's the ground right there. Something leaves the ground, it begins accelerating downward. That doesn't mean it's moving downward. If you throw something upward, it could be accelerating downward while it's moving upward. And what that means is it's just getting slower. So like if I go this way and at the same time I'm accelerating that way, I'm going to be going this way slower and slower and slower, and maybe eventually I'll turn around and start going faster and faster and faster. But it can happen. You can accelerate in the opposite direction that you're going. And anytime something leaves the ground, the acceleration is always negative 10 meters per second squared, at least in all of these problems. We're assuming that everything in these problems is in free fall, and free fall means gravity is affecting it and nothing else. So the acceleration is negative 10 meters per second squared. Negative 10 meters per second squared. Negative 10 meters per second squared. Same thing all the way around. Anywhere in this flight. I'm picking 1, 2, 3, 4, 5 points, but I could pick 1,000,000 points in there, and it would be the same until it hits the ground. Now, the reason this is negative always is because scientists, physicists, mathematicians, they've all decided that direction-wise, if something is moving to the right, we call that positive movement. If something is moving up, we call that positive movement. If something's moving down, we call that negative movement. If something's moving to the left, we call that negative movement. If you're familiar with graphing, this quadrant, you know, this side of this is the x-axis. Everything over here is positive. Those are positive values of x. These are negative values of x. On the y-axis, these are positive values, these are negative. So it's, if you're comfortable with that in math, get comfortable with it in physics. This negative just means that gravity pulls things downward. Everybody's okay with that. Somehow this business bothers people. So the negative just means gravity's pulling down. It's pulling down when you're going up, it's pulling down when you're going down. Slows you down when you're going up, speeds you up when you're going down. Because here it's working against you, there it's working with you. Still not ready for that graph. I want to do something else. Now this is a little bit weird. The thing goes up, it comes back down. So everybody knows that as you throw a ball up, it starts to slow down. Its speed decreases. And then it gets to some point at the top and it comes back and its speed starts to increase. So when it gets slower and slower and slower, and then it gets faster and faster, it's somewhere where it turned around right there. It had to stop for just a second. So at the top, its velocity is 0 meters per second. It's only that velocity for an infinitely short amount of time. It's getting slower, 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 then faster, 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 and it didn't just sit there at 0 for any amount of time. It kind of passed through it. And this graph will again get at that. Now, this is really the hardest thing on here. Once you believe that all those are negative 10 and you can just fill those in, those aren't hard. It's not hard to remember that's 0 meters per second at the top because it sort of stops and turns around. The 4 seconds, that's pretty easy. But this velocity, this is a little bit tricky. There are two ways to do it. One is just to think through it. If you know that the time at the top is 4 seconds, and you know that the ball is falling here, and it gets to the bottom at 8 seconds, then you know it takes 4 seconds to fall. From 4 to 8 is 4 seconds. And if you know the acceleration is negative 10 meters per second, that means you know, I could just write this, instead of writing negative 10 meters per second on all these, I could write them like this. I could write 10 meters per second squared. Sorry, I've been leaving out the squared. Downward. I could write 10 meters per second squared downward. Over here, 10 meters per second squared downward. 10 meters per second, sorry, second squared downward. 10 meters per second squared downward. That's just using a vector, using an arrow to show the same thing as what the negative is doing. And that might be really a better way to do it, because that gives you an idea that when you're going up, you're moving against acceleration, so it's slowing you. When you're coming down, it's helping you, it's giving you a push. So what was I getting at there? Oh yeah, so the acceleration here is 10 meters per second squared downward. So if you start to fall, and this is your acceleration. Acceleration means every second that much is added to velocity. 10 meters per second per second. So for every second, 10 meters per second is added. So during the first of those 4 seconds, you're going to add on 10 and your velocity is going to be 10. And during the second, you're going to add on another 10, so your velocity is 20. And then in the third second, you're going to add on another 10, so it'll be 30. In the fourth second, you add on another 10, so it's 40. So your speed is 40 meters per second. You're going really fast. And I could just put an arrow going downward, or I could write a negative here. Either one. So I could call this 40 meters per second and just put a down arrow. Same thing as the negative. I'll take that on a quiz. If I mark it wrong, tell me and I'll fix it. I'll give you credit. Now that we've got that, this part's easy. Since everything that goes down is the same, if the down part is the same as the up part but backward, then this is 40 meters per second also. But it's not downward, it's upward, so it's positive. And I could just write 40 meters per second up. That'd be okay. I'd take that. Now to this graph. Somebody was a little hung up on this today. I don't know if they were hung up, but I started to think that it's kind of hard to imagine passing through zero and not really spending any time at it. So I'm going to graph the velocity of this ball as it goes up and comes back down. I'm going to put it on my graph. So when it's thrown up, according to what I figured out here, it starts out at 40 meters per second, goes slower and slower and slower, and then it speeds up again, coming back down, speeds up, but has a negative velocity. So I'm going to start at a time of 0 seconds. I'm going to put a dot at 40. And after the ball's been going up for 1 second, it's going to slow down. Here's 1 second, it's going to slow down to 30. And then after it's been going up for 2 seconds, it's going to slow down to 20. So this is showing you this negative acceleration. As it's going up, it's losing that much. So after 3 seconds, now it's down to 10. After 4 seconds, it has no velocity. It's passing 0. After another second, it loses another 10. So after 5 seconds, it's starting to come down, and it's speeding up. But you can see if it's losing 10 every time, now it's in the negative velocity zone, which just means it's going down. And after another second, it's going to lose another 10. After another second, another 10. After another second, another 10. And then it hits the ground. So 8 seconds, we're at the end, it hits the ground. If I connect all my dots here, this isn't a really nice graph because I drew it by hand. This shows you that we've just got velocity constantly decreasing. That's just showing, this is showing an acceleration of negative 10 meters per second squared. That, or negative 10 meters per second. That's how much the velocity changes every second. We start with this velocity and we do that to it after a second. So we subtract 10, we subtract 10, we subtract 10 for every second. Hope that makes sense. Let's see, the next one, this is straightforward. I'll just show you what I wrote down earlier. Difference between average velocity and instantaneous velocity. Instantaneous is at one point in time. Average is calculated over a distance. So if you have a runner who starts right here and they run this way as fast as they can. I'm gonna see if I can make them look like they're running here. Oh, that's kind of weird. I don't know why that arm's up in the air. Now they're fast. So this person starts 0 meters per second, accelerates, and runs 100 meters, 100 meter dash. If they do that 100 meters in 10 seconds, then they're going an average velocity of 10 meters per second. But that doesn't mean their velocity right here was 10 meters per second. And it doesn't mean it was 10 meters per second right there. At the beginning, it might have only been 2 meters per second because they're still speeding up. And at the end, it's probably faster than 10 meters per second because they've got to make up time for when they were going slow earlier. So instantaneous is at one little moment here, but the average velocity would be over the whole distance. Free fall, all of these problems we're assuming to be in free fall unless I say otherwise. Free fall just means traveling under the influence of only one force, and that's gravity. Free fall assumes that there's no air resistance and the acceleration is always g, which is, you can call it negative 10 meters per second squared, or you can call it negative 9.8. And sometimes people specify that free fall means you're falling, but I don't know. Sometimes people imply that free fall is the whole time. You could be going up and down and you're still in free fall. I'd say it's got the word fall on it. But the important thing that I want you to say is that you're falling through the air or moving through the air, and the only force acting on you is gravity.